colored area here represents a future projection for the Arctic sea ice. So the Arctic Ocean could be sea ice free by 2050 based on our model. And actually back to 1896, a Swedish scientist argued that with the increase of the carbon dioxide concentration in the atmosphere, we could see the increase of the surface temperature. And particularly these changes could be more significant in the polar regions. So actually this phenomenon has been observed by us in the past few decades. As you see from this figure, the Arctic warming is almost twice as large as the global average. This phenomenon is called the Arctic amplification. So probably you may wonder, why are the temperature warming faster in Arctic than the rest of the world? The answer is sea ice. So the left figure shows the average monthly Arctic sea ice extent in September from the 1979 to present. The 1979 is the year that we started to have the satellite observations. So we can see this, the rapid sea ice decline in the Arctic. And the right panel here shows you the satellite image of how we observe the sea ice that I obtained this figure from the NASA satellites. Here we can see, clearly see how much sea ice has disappeared in the 2016 compared to the 1984. And if you focus on this part of this figure, that we can see the sea ice decline is even accelerating in the 21st century. So here, this figure shows you the spatial distribution of the sea ice decline from the 2000 to 2015 based on the satellite observations. So this figure was included in a paper that I published last year. So in this figure, the blue color represents the sea ice decline, and the red color represents the sea ice growth. So you can see here, there is a large area that has been experiencing the sea ice decline in the 21st century. But how does this sea ice decline is responsible for the Arctic warming? It's because of the reflectivity difference between the sea ice and the ocean. We call it bright sea ice versus dark ocean. So as you from this figure, when the sunlight comes in, if the ocean is covered by the sea ice, almost 90% of sunlight would reflect back to the atmosphere. However, if this ocean is not covered by snow or ice, the almost 90% of sunlight would absorb by the ocean and would warm the ocean surface and leading to more sea ice melting. So this kind of the amplifying effect that accelerates the sea ice decline and that lead to the Arctic warming. And how does this Arctic warming affect the weather or the climate in the mid-latitudes? Here I show you an example. So this figure that is the LaGuardia Airport. Actually, on the January 4th this year, I was stuck in the LaGuardia Airport in New York City because my flight back to Tucson got repeatedly canceled due to the extremely heavy snow and strong winds. At that time, the eastern United States was experiencing an unprecedented bomb cyclone, which brings a really cold temperature and heavy snow and strong winds. So the right figure shows here is the January temperature is below the average this year. So you can see here there's a weather system called the Polar Vortex that brings the cold air down to the south. So even the New Orleans has been affected by this cold weather. So how does it work? So the polar vortex actually is the weather system that is a large area of the low pressure, and we have the strong jet stream like the counterclockwise wind circulation that could confine this cold air within the Arctic. However, so actually this jet stream basically is driven by the temperature difference between the Arctic and the mid-latitudes. However, when the Arctic is warming faster than the mid-latitudes, So the wind used to like move really fast, but when the temperature difference becomes smaller, so the wind becomes like smaller. So this pattern becomes more wavy, and then the cold air. So this pattern could bring the cold air down to the south. So this pattern could significantly affect the weather and climate, especially for the winter in the eastern United States. And for the Arizona here, I think we could not ignore the heat waves. So this is like how many days that above the 100 degree in Arizona for each year. So here we can see from the 1991 to 2010 average, we have the 92 days that above the 100 degree. And then on the current trends, by 2016, we would have the 132 days above the 100 degree. And then by 2100, we would have these days up to the 163. So more heat waves means more gas. It is a huge threatening to the human health. So you may wonder what drives the Arctic sea ice changes and what is causes Arctic warming. So actually there were many factors that could affect the Arctic warming, probably from the land, from the ocean perspective. But since I'm the atmospheric scientist, so I would show how the atmosphere factors changes the sea ice, especially the sea ice decline. So normally we talk there are two factors could affect the sea ice changes. One is the dynamic factors that we talk about the summer storms in the Arctic, and also anomalous atmospheric circulation patterns, and also the sea ice motion that drift away from a given location. And we also have the thermodynamic factors that we talk about the temperature, the surface energy budget, or how much water vapor that we have in the atmosphere. So for me, I mainly focus on the thermodynamics factors to see, especially the surface energy budget affect the sea ice changes. And since the surface energy budget is highly linked with the clouds, so I would see how the cloud and the surface energy budget work together to affect the sea ice changes. So before I talk about how the cloud radiation affects the sea ice changes, I think the one important thing to know is how the cloud affects the temperature. Basically, the clouds have two roles. The left panel shows here, when the sunlight comes in, if the clouds are thick enough, they reflect back, most of sunlight back to the space, and just only few parts will transmit through the clouds and reaching the surface. So in this way, the clouds could reduce the sunlight and cause cooling. And another effect of the cloud is they can emit long-wave radiation that they can actually act like a cover that traps the heat near the surface. Especially, so this effect is more important in the Arctic because the surface is covered by the sea ice, so the surface is it's really cold, so the clouds can warm the surface by emitting the long-wave radiation. So I put the short-wave radiation and long-wave radiation here at above these two panels. If you don't understand the two terms, don't worry. You can just simply think that the short-wave radiation comes from the sun and long-wave radiation comes from the clouds. And another thing I think it's important to mention too is there is a seasonal cycle of the Arctic sea ice. So there's a sea ice extend from the January to December. So basically, we have the maximum sea ice in the winter time, and usually the maximum Arctic sea ice we have is in the March. Then it starts melting, and we have the rapid sea ice, the melting in the summer, and it reaches the minimum in September. And then it starts recovering in the fall and the winter season. So in this way, we think the September CS minimum is a really important climate indicator that because it tells us how much sea ice we have every year, how like the minimum sea ice extent. So my study, basically I just focus on the cloud and radiation properties from the March to June to see how the clouds and radiation during the spring and early summer affect the sea ice amount in the September. So that's just basically what is my study about. And so these are results from the paper I published last year as well. Here I show you it is a correlation pattern. I know it's a little bit complicated. I will try to explain in detail. That here I show the correlations between the September CS concentration with the cloud fraction and the long wave flux in March and April. If you can remember that long wave radiation comes from the clouds. So basically the long wave radiation and the cloud, they exhibit the similar signal with the September CS concentration. So here we can see the negative correlations here just means when we have the increasing clouds, so the clouds emit more long wave radiation that reach the surface. So this effect could warm the ocean surface and lead to more CS melting. That's why we have the less CS concentration in September. So that's what this negative correlation tell us. And then, so when we approach the late spring and early summer, the solar radiation, which comes from the sun, it becomes more important because we have the solar angle that becomes larger and larger. So in this way, the solar radiation becomes more important. So here I just show you the mechanism that we propose to see how the clouds and radiation affect the CS changes. So in springtime, when we have the increasing clouds and long wave radiation, that which could warm the surface and lead to more CS melting. And in the early summer, the incoming solar radiation becomes more important, which would reduce the CS concentration minimum in September and leaving more open oceans. So that we have the more evaporation from the ocean surface. And then so we have the higher atmospheric moisture content in the following spring, which could form more clouds and have more long wave radiation. So in this way, this mechanism could create a positive feedback loop that accelerates CS decline. So when I see the positive feedback, that just means they could this just amplifying effect with each other. It doesn't just mean good. It's just they can just amplify each other to accelerate the CS decline. And another topic I have been working on is the melt onset problem over the Arctic. As I mentioned before, that there's a seasonal cycle of the Arctic sea ice. So the Arctic sea ice normally starts melting in March, but actually these days could be different year by year. Sometimes it happens like earlier, sometimes it happens later. But from the climatology, we can see this negative trend of the sea ice melt onset dates. So it tends to happen to earlier and earlier, as we see from the satellite observations. So this is highly correlated with the September CS minimum. So that means the melt onset date of the Arctic sea ice is really important for the September CS minimum. So my study here is to see how the cloud and radiation affect the date of the initial melting of the Arctic sea ice. So due to the limited time here, I just want to show my conclusion here. So for the early melt onset, it is usually driven by the large-scale atmospheric circulation that we would have the enhanced storm activities bring the warm and the moist air from the south into the Arctic, which would increase the clouds and also the water vapor, and this could increase the surface long wave radiation that would trigger the CS melt onset. But for the late melt onset case, And we found the solar radiation is more important for the CS melt onset, especially when the melt onset is happening in the June. That is the time we have the strongest incoming solar radiation. But probably you may also want to know what would happen in the future. So here I want to show you the CS decline that under the RCP 8.5 scenario from the 2000 to 2100. And if you just focus on this black thick line, you can see the rapid CS decline in the 21st century. So the RCP 8.5 is the emission scenario that defined by the IPCC, the Intergovernmental Panel on the Climate Change, that we have the different emission scenarios based on our different socioeconomic patterns. So the RCP 8.5 is the most aggressive emission scenario, that we have the high demand of the energy, and we have this rapidly increasing of the carbon dioxide concentration in the atmosphere, and we don't consider any climate policy in this scenario. So this is the worst case we could have. So yeah, for this case, we could see we probably would have the CS-free Arctic around the 2060. And for under this pattern, we want to see how the cloud and the radiation affect the CS changes in the future. So here I also showed you the correlation between the long wave flux and the September CS concentration in the early 21st century, middle and the late 21st century. And here I just show you the different months from the March to June. So for the May and June, there's no much difference. So if we just focus on the March and the April, we can see these negative correlations become stronger as we move to the late 21st century. So here we conclude that the impact of the cloud and radiation properties on the CS melting tends to shift to the early spring in the middle and the late 21st century. So to summarize my study, first I just document the spatial and the temporal features of the cloud and the radiation accompanying the melt of the Arctic sea ice. So this part I mainly focus I use satellite observations, and then identify the dynamic triggers of the Arctic sea ice initial melting, like what is important for the melt onset dates for the Arctic sea ice. And also, currently I'm working on this part. I use the Earth system model to test the cloud radiation sea ice feedback mechanism to see how it affects the sea ice changes in the past, present, and future. So the ultimate goal of my study is to improve the simulation and prediction of the Arctic sea ice changes. Here I just wanna, probably it's hard to see, but actually there's just IPCC special report like global warming of 1.5 degrees C just released 2 or 3 days ago. And I quickly went through the whole report to see what it tells us. And I grabbed this figure from this report. So basically just tell us that we're facing a really urgent situation. So whether we have the low emission or high emission or even the net zero emission could affect how our planet would be in the future. So yeah, so we see that the CS decline, they probably would have a different trajectory when we do the future projection. But how we would go, which trajectory it would follow, the choice is ours. Yeah, it depends on what kind of climate policy or what kind of actions we could take to just to protect our planet. Thank you. So, any questions?
As a climate scientist, I'm wondering if you feel somewhat frustrated working in the United States which is a country that seems to not grasp that concept of what's going on very well. But I'm also wondering if your projections, which you project in terms of ice in the poles, is something that doesn't hit people in their lives very well in 2050. And if there are economists who are doing projections of what the effects, what the results of these changes will be on the economy and people's lives, and if those people are reaching out to climate scientists as yourself to try to weave in your models with their economic models in terms of understanding the economic impacts of, as well as political impacts to all those things. Do you get any feedback from that world?
Yeah, actually, so back to your first question.
Yeah.
Actually, I would say, actually, I'm not a person like working with like the policymakers or even or other stakeholders. I'm a pure scientist. But I would say in the United States, we still have lots of really smart, really good scientists to work on this topic. There are lots of scientists, lots of good people that really care about this issue. Yeah, I would say like probably maybe in this topic, I'm a really good like probably the leader on this topic in the United States. So I feel really lucky. Yeah. So back to your second question, that actually, I didn't have many chances to talk with other like maybe economists or maybe like people working on the social science. But so for my roles, I think the reason I want to do the PhD in animal science is I want to provide the solid science evidence to the policymakers to tell them what is happening and provide the suggestions for them to say what we should do in the future. But I think just everyone should work together on this issue. But for me, it just provides the science evidence. That's my job. Yeah. True.
Is the same thing happening in the Antarctic?
No, it's not. So Antarctic is another story. Yeah, it's more complicated actually. In the past few decades, actually the Antarctic is we see a little bit increasing of the sea ice in the Antarctic. The reason is that, so you know the greenhouse gas emissions, so we talk about the anthropogenic forcing. It's mainly just based on the northern hemisphere. So yeah, we could see this impact is mainly happening in the northern hemisphere. That's why we see the rapid Arctic sea ice decline. Yeah, but not in the Antarctic.
Thank you for your talk. I have two questions. One very, I think, specific to your research, and then one a little more sort of outside. I don't know if you want to answer the second. The first one is, can you talk about, or does your research encompass types of clouds and their altitude and the atmosphere? And then the second question is, there are serious scientists talking about using ocean water sprayed into the marine cloud layer in the Pacific to reflect more light from that. Is that something that could apply to the market? It would be a mechanical intervention in the climate process to try to cool things down. Are you aware of research Arctic specific? So that's the second question.
Yeah, so your second question will talk about some recent like geoscience techniques that we can modify probably the reflectivity of the Earth's surface that can reflect some sun, maybe the solar like heat like back to the space. when I went to some conference this year, I saw some people working on that issue. So now the people working on this topic, they're mainly focused on the model experiments. As far as I know, there are no people really doing that in the Earth. They just try to probably do this experiments in the coming model to see how much impact it would have. Yeah. So it might be a good way to just mitigate the global warming issue in the future, but we still need lots of experiments especially in the model. Yeah.
But then on the first side, are there different types of cloud types that you look at more specifically?
Yeah. I indeed look at different types of clouds, how they affect the CS. So in the Arctic, we mainly focus on the low clouds because it takes up almost like 60 to 70% of the total clouds. So we mainly focus on the low clouds. So there are no much difference like when we look at the low clouds or total clouds because that's just the most of clouds are in the Arctic are just low clouds. So, yeah. Mhm. No other questions? Okay. Rachel?
What's the next thing that you're working on?
Sorry?
What's the next thing that you're now working on?
Yeah, now I'm working on this part to test. So I'm not sure if you remember this loop that I talked before, like this, I call this positive feedback loop. So this is, right now, this is just our hypothesis. So we need to use the Earth system model to test this hypothesis, whether it is true or not. Yeah. So in this summer, I was working with the scientists in the NCAR, the National Center for the Atmospheric Research. I work with the scientists there to use their model to fully test this mechanism.
Cool. Thanks, everyone. There's another Science Cafe here in November. The information's in the pamphlet. And another quick reminder, please fill out those surveys if you'd like to.